Hey, welcome back to the Intro to Internal Combustion Engine series. This lesson objective is to describe engine knock and the conditions that create it. You can find a brief description of engine knock and its contributing factors in section 13.2 in your textbook. For your notes, though, let's get some words down on paper. So let's start with the definition. What is engine knock? Engine knock is the audible tapping or pinging sound that you may hear coming from an engine. It occurs in spark ignition engines only. So what causes it? Well, there's many contributing factors. There's a few contributing factors, but there's one real cause, and that cause is the premature combustion of the fuel-air mixture, also known as autoignition. And you may be thinking to yourself, I've heard that term autoignition before, and I thought it was a good thing. That's true in a compression ignition engine. In a compression ignition engine, the engine operates off the premise of autoignition. However, in a spark ignition engine, remember, we want that spark to introduce the necessary activation energy to initiate that chemical reaction that we call combustion. We don't want it to happen on its own. So what influences autoignition or knock? A high compression ratio is one factor. The next is the use of low octane rated fuel. In other words, an octane that is lower than the required octane for that engine. Or incorrect engine timing, known as spark timing angle, meaning we're sparking too early. We'll talk about each of these in depth in some subsequent slides. So what's the effect of engine knock? Why is it a bad thing? Okay, it makes a noise, but what does it do? Well, it reduces your fuel economy. It introduces vibrations that will cause wear and tear on your vehicle. And more importantly, it could damage the engine and the emission control system. So on the right-hand side here, you see a few pictures showing some effects of severe engine knock. On the top, you see things like piston melting and cylinder bore scuffing. You can see exhaust valves melting, gasket leakage. And on the bottom right, you see the third piston from the left actually has its connecting rod that is bent. Clearly very expensive and not ideal conditions. Let's first investigate how compression ratio can contribute to knock. Remember, the compression ratio is the ratio of the maximum volume to the clearance volume, or the volume at bottom dead center to the volume at top dead center. Now think in terms of ideal gas laws. Yes, this is a mixture of air and fuel, but think about in terms of ideal gas law. If that compression ratio is too high, then the pressure is too high, then the temperature becomes too high, and it could be higher than the auto ignition temperature of the fuel that you're using. Okay, so what happens is a secondary flame front is formed. Typically, this flame front forms on the piston head or some other hotspot. Remember, it's not just that increased temperature of the air because of that compression ratio, but you've had repeated flames because this is a cycle. This is happening thousands of times in a minute. So you have heat transfer to the piston head or to the walls of the cylinder that are already hot. Now add that with that high compression ratio, that high temperature from that compression ratio, and you create hot spots where secondary flame fronts are formed. What's the problem with that? Well, you have a flame front that is generated by the spark from the spark plug, and it will collide with a flame front generated from a hot spot in a different direction, which is not conducive to pushing the piston down. And when they collide, you get knock. Let's next investigate octane. So you've probably been to the gas station, presumably, and you've seen multiple octanes that you can select for your fuel type as depicted in the picture in the top right. And you probably think, or many people erroneously think, hey, if I put a higher octane fuel than my car requires, I'll get better performance. Well, is that really the case? Let's investigate that a little bit. So first, let's define what an octane rating is. An octane rating is a measure of a fuel's ability to resist premature combustion, also known as autoignition. Higher octane, in simple terms, means it is more resistant to burning. It does this via different complex carbon chains in the fuel mixture. Okay, so when do I require a higher octane fuel? Well, you require higher octane fuel in higher compression ratio engines. We just talked about the compression ratio. If I make that fuel more resistant to burning, it's less likely to auto ignite. Okay, typically when you're using a supercharger or a turbocharger, you remember those from your steady flow devices. We'll talk about them again later in the course. you have an associated high compression ratio. So you can get the max amount of air and fuel to get the max amount of energy out of that engine. So will a higher octane fuel give you improved performance? Well, that depends. Okay, so under normal driving conditions, it has little to no benefit. So if your car requires 87 octane and you put 92 in it, you're just throwing money down the toilet. However, if you have a vehicle that you can tow things with and you have periods where you put it under a heavier load or has variable conditions under which it runs, sometimes you can see an increase in mileage when you're using a higher octane fuel, but probably not worth the money that you're spending on that fuel. So what if I use a lower octane fuel than is required? What if my car calls for 92 octane? I say I'm going to save 20 cents a gallon. I'm going to get 87. Well, in older vehicles, that's going to result in knocking or pinging. In more modern vehicles that have variable spark timing, then you're typically going to have reduced engine power and reduced fuel economy, but it can also result in knock and it can still damage your engine. Most importantly, if you care about your wallet, if you use an octane that is lower than what the manufacturer requires, you're going to void your warranty. Let's talk about spark timing angle and how it contributes to knock. So recall figure 13.2, which shows the conversion of linear piston motion to rotating crankshaft motion. You can see that there is an angle associated with the crankshaft relative to the vertical or linear position of the piston. I think it's a little bit easier to see in an animation, so let's move on to an animation. So here we have the CAD animation of the piston moving in the cylinder, taking linear motion and converting it to rotational motion of the crankshaft. We're going to freeze frame it here at the top. And if I take that top position when we're at top dead center and I draw a line, we can call that our datum. Now, remember, this piston cylinder is moving up because the crankshaft was rotating clockwise. So again, if I draw that datum and I draw a line along the crankshaft, the angle between them is my angle before top dead center. Now, conversely, as my piston begins to move down, again, the crankshaft is moving clockwise, is rotating clockwise in this figure. And again, I draw that datum and I draw a line through the crankshaft. The angle that makes is my angle after top dead center, so ATDC. Let's show it again with the animation. So angle before top dead center, after top dead center. Okay. So when do I want my spark to actually ignite? Well, I want it to happen sometime before top dead center. But if it sparks too early before top dead center, my piston is still going to be moving up while that flame is propagating away, and it's going to have opposing forces which are going to create knock. Well, why don't I just do it at top dead center, you say? Well, at top dead center, that flame is only moving so fast, and that piston is already about to start its downstroke. So it's a little bit too late, so I'll lose power. If I spark at top dead center or after top dead center, I'm propagating a flame in a piston that's already moving down either due to counterweights or another piston that is in phase with it. So I want to spark here before top dead center, but not too early. When before top dead center depends on the engine. This is a great image that you can freeze. I'm going to go through it very quickly. That depicts different angles before top dead center and after top dead center associated not just with spark, but when the exhaust valve and the intake valves open and close on a typical reciprocating engine. Okay, this wraps it up for your description of engine knock and the conditions that create it. If you have any questions, please see your instructor.